an Associate Professor Emeritus in the Department of Integrative Physiology at the University of Colorado Boulder. He earned his PhD in Organismic and Evolutionary Biology from Harvard University, after which he completed his postdoctoral training at the University of California, Berkeley. Dr. Kram is internationally recognized for his expertise in the mechanics and energetics of terrestrial locomotion. What is fascinating and particularly unique about his research is his comparative and evolutionary approach that spans from studies on load carrying in rhinoceros beetles, walking in elephants, hopping in kangaroos, and waddling in penguins, to what he is most well known for, bipedal locomotion and cycling in humans. Dr. Kram has published 113 peer-reviewed articles that have been cited over 15,000 times, including 20 articles cited over 200 times and 45 articles cited over 100 times. Today, Dr. Kram will discuss how 3 biomechanical factors affect elite marathon running performance and how Eliud Kipchoge's incredible sub-2-hour marathon performance optimized some, but not all, of these factors. A few housekeeping items before he begins. If you have questions during the talk, please post them in the chat. After the talk, you can also raise your hand and I will call on people to ask their questions. Also remember that we have reserved a 1-hour period after the talk for everyone to meet the speaker and ask him questions in a less formal format. This talk will be recorded. It looks like it's already started. Thank you, Mike. As a disclaimer, we ask that you please do not redistribute the talk or any of the slides from the presentation, but use it solely for your educational purposes. Please join me in welcoming Dr. Rodger Kram.
Oops. Okay. All right. Thanks, Chris. I guess this is a good excuse to wear a shirt with a collar and a button. I had to remember how to do that actually this morning. I need to start by disclosing potential conflicts of interest, and that is that I am a paid consultant to Nike. My lab has done research sponsored by Nike, and I also consulted for the INEOS 159 challenge just a couple days there. I really like it when people, I'm fascinated, I guess you could say, by people who do impossible things that some people think are useless, and particularly ones that combine technology and ingenuity and some athletic aspects in some things. So I think the motor control aspects of the Wright brothers has been highly underappreciated. Another example of such a thing is the first ascent of Mount Everest. This involved a remarkable amount of exercise physiology beforehand and some technology. As you can see, the bottled oxygen in the mask. It wasn't a COVID mask back then, it was an oxygen mask, and obviously accomplishing something that had never been done before. Roger Bannister did some exercise physiology experiments on himself prior to breaking the 4-minute mile, certainly an athletic accomplishment as well. Armstrong and Aldrin, first people to walk on the moon. Of course, their locomotion was of interest to, I can't admit that it was to me, I was only 8 years old, but locomotion on the moon was interesting, but of course, it was performing an accomplishment that required remarkable technology, including a computer with 4 kilobytes of RAM. This one may become more obvious later, and that is that sometimes these impossible tasks with technological assist eventually become possible without the technological assist. So Messner and Habler were the first ascents of oxygen without supplemental oxygen in 1978. It took quite a few years since the 1954 first ascent. This was one of my favorites when I was in high school, and that is the Paul McCready's team made human-powered airplanes, and one of which was the Gossamer Albatross, which flew across the English Channel. This also involved a lot of exercise physiology because it was a clear canopy, I suppose you could say, and with no airflow. So it was a heat and dehydration challenge as well as aerodynamic. But again, something that seems impossible, but also kind of useless. I mean, this has not really become an industry where people fly human-powered airplanes for good reason. And another example is, of course, the focus of my talk, and that is Eliud Kipchoge being the first human to run the marathon distance in under 2 hours. But if you step back for a second, and it may not seem useless, certainly seemed impossible, and in some ways the 2-hour marathon is completely random or arbitrary. The original the run for which marathons are named was from Marathon to Athens, and is approximately 40 kilometers. But in 1908, the Olympic Games were in London, and the lovely Queen Alexandra declared that the Olympic marathon should start on the green of Windsor Castle, and it turned out that it was 26 miles and 385 yards away from the Olympic Stadium. And that became the Olympic and subsequently the official marathon distance. So if we divide 42,195 meters by 7,200 seconds, we don't get a really round number. It's 5.86 meters per second, 21 and change kilometers an hour. So it is a seemingly random or arbitrary barrier to run it in 2 hours. If we were still running 25-mile marathons, the 2-hour barrier would have been broken long ago. But nonetheless, I think that even if it is arbitrary, it can be useful. And as Kennedy said in 1962, only 7 years before Apollo astronauts landed on the moon, we choose to go to the moon and to do these other things, not because they are easy, but because they are hard, because that goal will serve to organize and measure the best of our energies and skills. And I think this focusing aspect of these impossible and perhaps useless goals are not so useless, right? We've had a lot of, it can focus the interest of scientists, it can inspire the next generation of scientists, and it stretches our athletic limits in the case of Eliud Kipchoge, but it also stretches the limits of what we can do with science. In 1991, the world record for the marathon, which seems remarkably slow now in contrast, was 2:06 in 50 seconds. And Michael Joyner, an anesthesiologist and scientist at the Mayo Clinic, had a modeling paper where he said and calculated that if one individual could somehow have a very high VO2 max, 84 mils per kilogram per minute, and a lactate threshold that at a rather impressive 85% of VO2 max, and be efficient to have a sub-maximal oxygen cost at marathon pace of 179 milliliters of oxygen per kilogram per kilometer, that person could run a marathon in under 2 hours. And of course, this was derided as being impossible and perhaps useless. But it's now just about 30 years later, not impossible. More recently, last year, it was finally reported, and it came out in Journal of Applied Physiology this year. Andrew Jones's group, combined with the Nike Sports Research Lab, studied 16 elite marathon runners who they were candidates for their attempt to break the 2-hour marathon. And they were their average time was basically the world record that it was when Joyner was making his model. Jones pulled these athletes together at the Nike campus and also at his university and measured their VO2 max. It was remarkably not as high as I would have expected, and has been a little bit controversial, I have to say. They had a high lactate thresholds. They could run at almost 19 kilometers an hour without accumulating lactate, and that is 83% of their VO2 max, similar to what Joyner was proposing. And perhaps the most interesting to me, definitely the most interesting to me, was that 7 of these athletes could run at marathon pace and be in a steady state. Their oxygen consumption was stabilized, and that was at 95% of VO2 max. So that was quite remarkable. As interesting as the high values, for me, is the distribution of the values. Oh, sorry. We can see that these are individual data points with a red line indicating the mean value for the group. And indeed, there are individuals like Joyner was identifying who have very high VO2 maxes. There are individuals who have a very high lactate threshold. And there are individuals who are remarkably efficient. The lowest circle over here is using very little energy to run at. This is not at 21 kilometers an hour, but it's close. So Joyner's idea was that if you get one person who had the best of each of these three categories, they would be able to run under 2 hours for the marathon. But as I said in the quote, as I've highlighted in the quote, athletes who are more economical runners have lower O2 cost. They tend to have lower VO2 peak values and vice versa. So it's not easy. It's quite rare. It's unicorn status to have all three of these variables at elite levels. Now, biomechanics has no effect on VO2 max or lactate metabolism, but it can affect running economy, and that's where I'm going to focus today. Running economy is defined as the steady state submaximal rate of oxygen consumption at a standardized speed. The previous slides have calculated a cost of transport or a cost per unit distance. I find it easier to just use the rate of oxygen consumption. And this is an important slide here. This is really underlying all the work that we've done, and that is that if we can decrease the rate of metabolic energy consumption at a specific speed, in other words, make someone more economical, require less energy to run at a given speed, then they can respond and increase the sustainable running speed. In other words, they can run faster with the same physiology. So let's start with a baseline for Eliud Kipchoge, the man who eventually ran under 2 hours. Between 2013 and 2015, Kipchoge 4 times ran a 2:04 marathon, 2 hours and 4 minutes. And he did that on several courses, but most commonly in Berlin. So I consider that Kipchoge is a 2:04 marathoner under the previous conventional conditions. A year later, Kipchoge ran 2:03 at the London Marathon, and it might have been 6 months later, but anyhow, he ran 2:03 at the London Marathon. It was a very competitive race. He probably didn't run as fast as he could because he was worried about finishing second. Instead, he seemed to cruise along, and then with about a mile to go, really take off. But one of the most notable things for this talk about this marathon is that he wore a prototype shoe of the Nike Vaporfly, which I'm going to talk about a fair bit. In 2017, Kipchoge ran as part of Breaking 2, which was Nike's effort to have at least one athlete run under 2 hours for the marathon. And this involved nutrition and training monitoring and the new shoes, and also aerodynamic drafting, which did not correspond to the regulations of the International Athletics Association at the time. And he came desperately close, 25 seconds short of breaking 2 hours. The other feature of this attempt was that it was run in Monza, Italy, on an auto racing track with big, wide, sweeping curves. In 2018, Kipchoge ran 2:01:39, essentially in a conventional race without additional drafting, without additional pacemakers and drafting. And he ran solo for most of the race because no one else can really run this fast. And he had on what have become known now as super shoes. And he ran what is the official world record now, 2:01:30. 1:39. And then finally, in October of 2019, Kipchoge did break 2 hours in Vienna with a similar approach of having runners who ran in front of him, breaking the wind, and rotating in and out, so that there would be teams of 6 or 8 runners who would break the wind for him. And then once they got tired, another crew would come in and pace him and break the air resistance for him. So to paraphrase the Matt Damon's character in The Martian, to get from 204 to 159, I'm going to have to biomechanics the heck out of this. So how do we get from 204 to 159? I'm going to talk about course design, aerodynamics, and shoes. This is the course map for Berlin, where Kipchoge set the world record. And the first thing that occurs to everybody is, man, there are a lot of turns on that course. It's just, it almost looks like a maze. And we wondered how much the curves, eliminating curves, could improve marathon performance. So my former PhD student, Paulo Taboga, who's now a professor at CSU Sacramento, and he and I started to make a model of how curves could affect distance running, not sprinting, but distance running. So when a person runs along a curve, they have to lean into the middle, into the center of the circle, and as a result, that's so that they can exert an inward force on themselves, and in effect, they end up being heavier, right? It's as though gravity was increased, and the axial force, this F bar sub A, the average axial force, is proportional to the velocity, the tangential velocity, and you can see that it's also an important factor is the radius of the turn. Okay, so if you're heavier, maybe this isn't a surprise to most of us. If you're heavier, it increases your metabolic cost of running. This equation is perhaps gratuitous, but it is the equation we used for calculating how much oxygen consumption would increase if you were running along a curved path at a certain velocity rather than in a straight line. And we came up with this equation based on experiments where we lifted up on people and essentially reduced gravity, and then we extrapolate from reduced gravity to a slight amount of hypergravity. This is a cool photo from the Monza racetrack where the athletes ran breaking 2. This is the famed curva parabolica, and it's obviously got the wrong banking for a person running, but it was the choice of Nike's team to pick this race course. How much do curves affect distance running speed? Well, we chose to sort of make our baseline the 400-meter track and used Kipchoge's world record time. If instead of running, which would be unpleasant, I admit running 26 miles on a 400-meter track would be unpleasant, but just for theory, if they then ran on a 200-meter indoor track with tighter curves as shown in the upper left corner, it would only be about 21 seconds slower, according to this model. And we tested this model using indoor versus outdoor track performances and found that it was working it's quite accurate. If we then, instead of on a 400-meter track, ran in a straight line, we could run only about 7 seconds faster. So curves are not really the most important thing. We calculated that the curves of the Monza breaking 2 course only imparted a 1.5 second penalty compared to running in a straight line. And running in a straight line has its own other challenges, and it's not allowed by the rules of athletics, international athletics governing bodies. You have to finish within half the distance. The finish line has to be within half the marathon distance of the start line. So Kipchoge wouldn't have run much faster in breaking 2, only a 1.5 seconds faster if it had been a straight line course. But that's not the only aspect of a course. Uphills and downhills can be far more important, as we've learned. This is a gratuitous Colorado slide. There is a marathon that runs up and down Pikes Peak, up from 6,000 feet to 14,000 feet in elevation. Very good marathoners run this, and yet the course, they can probably run 2 hours and 15 minutes. They take about an hour longer when you have to run up to the top of the mountain and back down. Of course, the Monza course was nowhere near it didn't involve very hills anywhere near Pikes Peak, but it did involve, in particular, one hill in this section of the track that climbed 4 meters, a little over 4 meters, and a few other, this straightaway, it seems perfectly flat if you're in a car going 200 kilometers an hour, but if you're running, it's not insignificant as we've calculated. So basically the course is uphill for this top part, and then a gradual downhill on the finishing straightaway. So I got together with a bunch of former students and also a new colleague from the University of Vienna to try to calculate how much penalty the Monza course imparted based on the elevation changes. And we also, you might start to guess why I recruited Christoph Triska from Austria, and that is we also wanted to analyze the Ineos 159 challenge when the 2-hour marathon was broken. Oh, let me just go back and brag, since I don't have any pictures of grandkids, since I don't have any children or grandchildren. But my former student, Chris Ariano, just heard this morning and told me that he received an NSF Career Award. So I'm super pleased about that. Okay, we used an equation that we based on treadmill running on small uphills, and also another study that is not as precise for slight downhills. But when we did that, we found that the small hills on the Monza course, going over them repeatedly, there were many laps involved in the breaking two, was about a 47-second penalty. And if that Monza track had been flat as well as straight, we think that Kipchoge would have broken 2 hours, and he would have run a time remarkably close to what he did run in Vienna. So that dream team of mine, I pulled together at the last minute because the course for Ineos 159 was not announced until, I believe, 2 weeks before the race. So we said, let's see if we can crunch the numbers on Vienna course in time. And this is when Christoph Triska, he was the perfect person. He's an exercise physiologist at the University of Vienna, and he's a triathlete, and he has a Garmin GPS watch, and he went out to the course and got measurements of the elevation changes with better precision than we could get from the maps, and we evaluated the course in Vienna. The Vienna course has one important thing that wasn't initially announced. We had to adapt it, and that is it started on the Reichsbrücke, the Reich Bridge, and it drops 14 meters in elevation in the first kilometer. It then goes on to this long straightaway. It's about 2.5 miles long and 5 miles as a circuit. And this is a beautiful place to run. It's nearly flat, and it's tree lined, and there's spectators. But what worried me was the turns. The first turn, the Lusthaus, it looked awfully tight on the map, and the second turn of this circuit, the Praterstern, didn't look so bad. But over this basically 2.5 mile straightaway, the elevation change was only 3 meters, plus or minus 3 meters. So it was much more gradual than the Monza track. The turn radius at the Lusthaus corner, the roundabout, was only 23 meters. And a outdoor track is somewhat tighter than an outdoor track, a little bit wider than an indoor track typically is. Our calculations showed that in that first drop off the bridge, provided about a 6 or 7 second benefit compared to a flat course. And then every lap, because of the ups and the downs, was incurring about 1.5 seconds of penalty per lap. So as a result, this course was nearly perfect. It was only about a second slower than a perfectly flat, straight course, and yet it was beautiful. It had fans next to it, and there was almost no wind on that day, and there's hardly ever any wind there because it's a tree-lined corridor. So almost a perfect course. If they if organizers of a race like this wanted to optimize it and stay within the rules, dropping 42 meters is the limit, 1/10 of 1% of the distance. That would save somewhere between 25 and 28 seconds. So there's still some room for improvement in the course and still staying legal. Okay, aerodynamics. Kipchoge ran essentially solo in Berlin, but in breaking 2, he ran behind an arrowhead of pacers and windbreakers. And in Vienna, for the Ineos 159 project, they did computational fluid dynamic modeling and figured out that this pattern, this sort of inverted arrowhead, and with 2 runners behind him, presumably giving him a little bit of aerodynamic push, was optimal. And we have not been able to get any, even though I consulted for Ineos, I've not been able to get any more information about the wind tunnel testing, and they haven't published it, which is kind of hard to understand. This is a beautiful drawing of what computational fluid dynamic modeling the results look like. You can essentially measure the force acting on each surface of the person. This is all well and good. It requires cool supercomputers. You can move the runners around into different patterns. You can try different things. You can put a runner behind. You can have them run in a straight line. It's extremely flexible, but there's really no way to translate from the reduced aerodynamic resistance as to how much it reduces metabolic cost. And therefore, it's very hard to, it has been hard to convert to a metabolic cost. So, I had a pleasure of having a visiting student a graduate student from Brazil, Edson da Silva, and he and my postdoc at the time, Walter Hoogkammer, worked on this project. And we used equipment that was familiar to anybody who's looked at previous research from my lab. We had rubber tubing and pulleys and a treadmill that measured forces, and we also measured their rate of oxygen consumption. And we pulled backwards with small forces. And we had to, you can see that over here, this is indicating that our apparatus was 6 meters tall. It went up through the ceiling of our lab into the open space of the gymnasium where we are. And that was necessary in order to keep this applied impeding force nearly constant. By having a long piece of rubber tubing with a small weight hanging from it, we could apply a very constant force to the person. And we chose to use forces that were comparable to what all the measurements, the computational fluid dynamics measurements, say the impeding force is. And that's about 1% of body weight. We studied 3 different speeds, 12, 14, and 16 kilometers an hour, and no pulling back force, a medium pulling back force, and a higher pulling back force. And it's expressed here as a percent of each runner's body weight. So there's, of course, some variation in body weight. Let me boil those data down. The colors are just indicating different speeds. And fortunately, the data collapsed and compressed, which makes life easier. So here we have the change in the metabolic cost of running plotted versus the horizontal impeding force expressed in body weight. The solid line, which is the regression for all the data, suggests that at 1 body weight of aerodynamic resistive force, if we could completely eliminate any air resistance, it would improve running economy by about 6% on average. But the other interesting thing here is that it's not the same for everybody. Some athletes apparently use a lot more energy to overcome air resistance than others do. So some people get a big change when they're drafting, and other people don't get as much. A 6% improvement in running economy, because the metabolic rate is not a linear function and it doesn't have a zero intercept, it's not exactly a one-to-one relationship. It's sort of like 2 for 3. So if in this graph, we reduce the energy required to run by 10%, which would be a lot, at marathon speeds like the 2-hour marathon, it would be about a 6 or 7% improvement in velocity. So a 6% improvement, which is what we would see if all aerodynamic drag was removed, would translate to about a 4% faster running time. And this is from a paper by my former student, Shalea Kipp. And this is how happy a person looks when they make an Olympic team. But she actually looks about that happy most of the day, I have to say. The drafting used in Breaking 2 and also in Ineos is not allowed by the rules of marathon competition. But my former students here again have done some modeling of what we call cooperative drafting and a rotating pace line. So if you had 4 very top elite marathon runners, a bunch of 203 runners, if they ran and had a pact, an agreement that I'll run in front for a minute, and then I'll go to the back, and this guy will run in front for a minute, and then he'll go in the back, much like a cycling race, a breakaway in a cycling race would do, that could save as much as 2 minutes. It's not quite as much as having complete aerodynamic blocking, because there's also a penalty is the person who's up in front doesn't get the full effect of drafting, right? They're breaking the wind. They get it a little bit easier when they go to the back of the line. But this would be something I'd love to see take place in elite marathon running. There's another way to get around this, and that is to design a course that does the first half in a forest on a really windy day and run the second half with just a howling tailwind that pushes you for the last 13 miles or so. This would be technically legal. People might say it's not in the spirit, but it certainly is another way to break 2 hours for the marathon. And I didn't do any calculations here because it depends on what wind you choose. And you can pick a conceivable wind, a 20-mile-an-hour wind will get you there if you happen to be a 203 marathoner to begin with. Okay, I'm going to try to wrap up about shoes here. Clearly, 3 factors. We thought going into all this that 3 factors would be most important: the mass of a shoe, the cushioning of a shoe, and perhaps the flexibility and stiffness in longitudinal bending of the shoe. A long time ago, 1984, a scientist named Ned Frederick started the Nike Research Lab, and one of the first experiments they did was to see how much the weight of a shoe or the mass of a shoe affects things. And clearly, lighter shoes require less energy, but it's a very nice round number whereby 100 grams, if you take 100 grams off of each shoe, your running is going to cost you about 1% less, and that's pretty independent of speed. My graduate student, Chris Tung, followed up on this a lot many years later. And what we did was we put foam on the treadmill and had people run barefoot, so we could really control the cushioning aspect. We had people run barefoot and in shoes, but the barefoot is probably the most relevant here. Here we show, this is the change in metabolic power, where this straight line is someone running barefoot without any cushioning. And when we put foam on the treadmill that's 10 millimeters thick, they save almost 2% in energy cost. On average, people saved, if we go to thicker midsoles, people save 1% energy, but there's quite a bit of individual variation as well. Somebody's munching potato chips or something right now. Thank you. There's a lot of individual variation in this response to cushioning we found. Some people who were very keen on barefoot running actually used a little bit more energy when they had a cushioned surface, but some of us really love a soft ride and used less and less energy as the foam got thicker. Not long after, sorry, hello, question? A study from the University of Calgary, Darren's definition, the professor, the PI on this, put a carbon fiber insole into running shoes and found that there was a very slight metabolic savings, about 1%, and it was very difficult for them to derive that 1%. They had to be very careful about their experiment, but this was suggestive. And Darren's definition's PhD student, Gung Lo, who went to work for Nike, certainly was well aware of that study. And he was one of the lead designers of this famous shoe now, the Nike Vaporfly, which we called, at the time in our study, we called it the NP because it was a Nike prototype. It didn't have a name. This was made possible by the very low density, very lightweight foam, and foam that's extremely resilient. It has a great rebound. But the most controversial part seems to be this carbon fiber plate that's sandwiched in between the foam. We were contracted and anxious and delighted to test this shoe for the first time. We compared this shoe in 18 very good runners. They could all run under 10 kilometers, under 31 minutes for 10 kilometers. That's not easy to do. They all had to be size 10. And so we think that in North America, Boulder, Colorado is one of the few places where you could do this study. We make the joke that we had to find male Cinderellas who would all fit this shoe, but they also had to be excellent runners as well. And this is our dream team, most of whom I've introduced to you already. We compared 3 shoes, the conventional Nike shoe that Kipchoge used successfully to run 2:04 in, the Adidas shoe at the time, which was used to set the world record of just under 2:03, and this Nike prototype shoe. These are graphs of the foam, the properties of the foam itself, and it's being tested in a bench test, basically. And as the force increases, the material compresses or deforms. And the foam in the Nike prototype shoe, what became the Vaporfly, has a couple of important characteristics. One is it's very soft, and you can see that it moves to the right. It deforms a great deal under the same force, almost twice as much. And as a result, it stores a lot more energy. The mechanical energy stored is shown as the area under the curve. The other thing is that it doesn't throw away that energy. This curve on the loading side is very closely duplicated on the return side when the material is relaxing. So this is called, it has a very low damping. It has a high coefficient of restitution would be another way to put it. We tested these shoes in probably definitely the most careful experiment I've ever done in my career. We compared athletes at 14, 16, and 18 kilometers an hour. We had 18 subjects. We controlled everything about their physiology that we could. They had to eat the same thing. We weighed them after every trial and had them drink water so that they maintained their weight. We were really meticulous. And as a result, we were able to get very clean results whereby all 18 subjects used less energy to run in the Nike prototype shoe compared to the previous best shoe from Nike and the best shoe from Adidas. So the average was basically 4%. Again, interesting, the individual variation. Some people have very steep lines and some people have less steep declines. The individual savings ranged from less than 2% to over 6%. There were some people like to use the terminology responders, and there are certainly responders. But as I showed you earlier, even old-fashioned foam, there are different responders. So it wasn't anything special about the foam that made responders. We further explored the biomechanics to try to figure out why these shoes save energy. Here we have those results boiled down to the torque or moment at each of the joints and the mechanical power generated at each of the joints, the hip, the knee, the ankle, the metatarsal phalangeal joint, and also the energy the energy required to bend the shoe. So a lot of our hypotheses were wrong. We expected to see a lower knee joint moment and less power at the knee. Didn't see that. We expected to see a greater moment at the ankle, greater torque, because the shoe is so stiff. The shoe doesn't bend as easily. That was not the case. But we did see both less negative and less positive work at the ankle joint, and less work at the metatarsal phalangeal joint. The NP again is in orange. That's the Nike prototype shoe. So finally, everybody, when the carbon fiber midsole came out, the plate, everybody said, "Oh, it's acting like a spring." It actually is not really acting like a spring because it barely bends. Okay, it's a stiff object. If a stiff object barely bends, it's not going to store much energy. And it was really, I think it was 1/50th or 1/100th of the energy that would be elastically gained, stored in return from the ankle joint. So the plate's not acting like a spring. Okay, so at this point, if I was giving this talk a year ago, I would have said, like, there you go, we figured it out. But mind blown. My former student, now Professor Wouter Hoogkamer at the University of Massachusetts, and his technician, Laura Healy, did the audacious experiment of taking perfectly good, brand new $250 running shoes and slicing them with a saw. They put slices and cut the carbon fiber plate in one pair of these Vaporfly shoes, referred to here as the VF cut, as opposed to the VF intact. They measured 15 subjects running at 14 kilometers an hour, and they used the same amount of metabolic energy. Okay. Obviously, the shoe that they cut the plate could be folded like an old like a Nike Free, like a shoe that had no stiffening plate. And so the obvious conclusion is that the longitudinal bending stiffness of a shoe is not what's affecting the running economy in the Nike Vaporfly shoes. It's not acting like a spring. We knew that from the previous studies, but it's not really acting like much of a lever either. And I would say this is still not completely resolved and really controversial. It has not yet been published. It's available at Sport Archive. You can look for the name Hoogkamer. There's not a whole lot of Hoogkamers in the world. It comes up right away. Okay, so running shoes need to be light. This foam is really light. A good running shoe foam should be compliant and resilient. The Vaporfly foam, the Pebax foam, fits the bill for that. I think that's where most of the, if not the lion's share of the energy savings is coming from. And I used to say that the flexibility and the stiffness was important. And now I have no idea if it's important. I'm leaning towards that that's not the reason why the Vaporfly shoes work. Okay, how do we get from 204 to 159.40? Well, the course design helped. Having no curves maybe saved 15 seconds compared to Berlin. Wouter and my other students are working on modeling the map for Berlin to figure out how much slower Berlin is than a straight line. Downhill with minimal uphill certainly can save time. Probably the course in Monza lost about 40 seconds. Compared to Berlin, it's going to be more because Berlin does have more substantial hills. The aerodynamics can save up to about 4 minutes in a perhaps more in a high responder, and we don't know how perfect drafting can be. The shoes, the old Vaporfly, 3-year-old shoes, Vaporfly 4%, save somewhere between 1.5 and 4 minutes, depending on how much of a responder the person is. The Alphafly shoe, which Kipchoge wore in the Ineos project, we don't know. We haven't done any experiments, and I'm not privy to knowing how much energy the Alphafly saves. but Nike doesn't tend to make shoes that are worse as time goes on. So I would presume that they save more energy than the Vaporfly shoes that we studied. So this is a painting made by a friend of my student from Brazil. I just love it. It's got the aerodynamic birds here flying in a V shape. And I'm going to end here and take questions. Sorry, I ran a bit long, but there you go.
Thank you very much, Rodger. That was excellent. We are going to have time. You ran, I think, 1 minute long from what I asked, so that's pretty well prepared. And I think that's only because I waited for people to come in. So you did an exceptional job. There's plenty of time for questions. There weren't questions placed in the chat too much. There was one from Dr. Alex Ng. Alex, did you want to ask Rodger your question?
Sure. Thank you. Thanks for this great and very interesting talk. I appreciated the Habeler and Messner reference. And this has to do with your introduction slides. And to confirm one of the earlier, I believe it was a Nike study,